Welcome everyone, good afternoon. My name is Christian Linta. I'm an affiliate faculty in imaging science and the main department of biomedical engineering. And today is my great pleasure to introduce our guest speaker, Dr. Bill Higgins from Penn State University. Dr. Higgins and I think I've known Bill for about 10 years through the SPI medical imaging community. We've both serving on the same program committee for the past 5 years. As I've learned not too long ago, actually, Bill went to a postdoc in the same lab I did my postdoc. I was there in 2011, he was there in 1989, so that's about 2 decades apart. Bill got his undergrad degree in EE in electrical engineering from MIT, and then a master's and the PhD from University of Illinois Urbana-Champaign. He was actually President Munson's first PhD student, so last night we caught up with Dave Munson and this morning for a quick meeting. So it's always good to catch up after a number of years. And Bill's been at Penn State for about 30 years now, actually, and he's trained more than 80 students and postdocs in medical imaging and image processing, and a lot of his work has focused on applications of medical imaging and image processing and computing for bronchoscopy and for chest navigation. And this year he was actually named 2019 Inventor of the Year at Penn State. And congratulations for that. And we look forward to hearing your work on image-based planning and guidance of bronchoscopy of the chest.
All right, thank you very much.
Yours. Thank you.
Yeah, get over here. If I'm not speaking up, let me know. It looks like this is projecting okay. My domain is the chest. There it is. We use lots of images. We use non-invasive imaging, and we use endoscopy. And we're all about looking at lung cancer. That's a major killer, as I'll get into. And we do a lot of multimodal work in terms of planning and guiding these procedures using imaging. So this is a little bit about my talk here. I'll kind of talk about some of the fundamental things in terms of current practice and some of the things we observed there in some of our earlier work. And then the latter part, I'll talk about some of our newer work, and I'll say a bit about my entrepreneurial efforts as well. So this is kind of a big picture of what we involved with the lung cancer disease. The idea here is like we're trying to detect the disease, and then you want to come down here and then diagnose it. Do you have cancer or not? You want to stage it. Do you have a chance to get cured? If you do, you want to treat the disease. In order to get to that point, the radiologist comes into play first. They get a chest CT, and they'll look at a chest CT and they may find some region of interest, like a cancer, possible cancer nodule. And they'll have to then, if they see that there's something there that's suspicious, they have to somehow figure out some way through the airways to get to that site so that they'll take a tissue sample, a biopsy. That's going to be done by bronchoscopy later on. So CT, as we'll see, is the main modality for this, but there's other imaging, PET, we'll get into that we use as well. So after the procedure is planned, they can then go in and put the bronchoscope into the chest and follow the route that they plan to get to the potential cancer site. And they're using video to do this. So this isn't the best modality necessarily, type of information to be able to go through a complicated environment like the chest. So this idea of guidance is most definitely needed. But this is the picture that motivates everything that we do. So the disease, it's pretty good talking about this to get an idea of why this is so important and why there's so much interest here. This is the #1 cancer killer. 30% of all cancer deaths, over 1 million worldwide, very poor survival rate. This is because people tend to be found with disease at a late stage and there's no hope of cure. In the US, in terms of trying to do diagnostic work, after the imaging, they do about 500,000 bronchoscopies. This is just in the US. So there's a lot of procedures. It's a very prevalent thing that's done. Now, one enormous thing that's just happened in the past few years is the idea of a lung cancer screening test. There are tests already for women for breast cancer, there's colon cancer. Screening, just if you don't know what that is, it's trying to see if you might have the disease and you're not sick. So that way, you're not sick yet, and you have a chance to get totally cured of the disease. So it's good to go through a screening. They can kind of screen you. Then you can go on and then go through the diagnosis and staging and hopefully catch the disease at an early stage and have a better chance of surviving, better than this 15%. So with this thing happening here, this major event, this now means that there'll be millions of patients just in the US, tens of millions, that could conceivably become customers for this procedure. This number could go up. And not only will there have to be more patients in that, but the patients that we'll see will have less disease ideally, so the onus of being able to diagnose it is going to be harder. And so that kind of is a big motivator here, the big patient population and this notion that if we can't do things very well after they screen people, it's like they're wasting your time screening and patients are dying anyway. So we got a really great reason for having to do this. So the chest, CT scans, super high resolution. We have hundreds of sections. Sections are on the order of a 0.5 millimeter resolution. So we get spectacular anatomical data, much information here. You clearly see things. This is easy to see. The heart, you see the bones here, the spine, these airways. It's all very clear. Here's a real section of a heart, of a chest, and you can see the similarity, of course. So it's great for seeing the anatomy, CT. Some other language, some of you are probably familiar with it. A lot of you are working with images. You got this three-dimensional data, so we need to have 3D terms like coronal plane, sagittal, transverse. Working with 3D coordinates. The gray levels, as such, and it's called it's a Hounsfield scale, standard scale for CT, 12-bit scale, so you got a lot of resolution there. So kind of looking at the current state of going through this flow with trying to diagnose and stage and treat the disease. I mentioned that a patient first comes in to get a scan made, a non-invasive imaging scan. So the current practice is that the physician really kind of mentally goes about looking at the data and manually plans things. So I got a few things about that. So radiologists, they're really great at anatomy. They can spot things really well. They know their anatomy. So they're anatomical experts, but right now they'll scroll through this stack of data, which is quite a task, and try to figure out how to reach these cancer sites. So I kind of showed a slide here where they had to, I'm not going to back up to there, but they have to thread their way through. They got to use a CT to figure out how to get these routes. I do have a slide to show that. So they'll mentally try to figure out where to go. Here we are. So this task here is quite difficult, and we quantitatively, we've shown that they actually are not so good at being able to do this. So if they're sunk here, then they're not going to have a hard time with doing the later procedure. But let me just talk about how this goes. So let's just say you're randomly trying to track your way through the airways. You start in the trachea, go to the right main bronchus, it's a bifurcation, and continue on through several more bifurcations, get to this region of interest. By chance, just to go to a fourth generation, the chance of getting there correctly is 4%. Now, radiologists can do something. They actually are able to do better than 4%. But they actually aren't that great, nevertheless. This just kind of helps you see that the problem is very complicated. And a lot of the sites are way down here around generation 6, 7, 8, 9, and if you don't have any help, you're really sunk. But let me just say a bit more about this. One study we did a number of years ago, we had 14 physicians do a phantom study, and we only had them go to generation 4. We picked some sites, and they had a CT scan. They could take as much time as they like, and they had to sort of figure out where these sites were. Well, for these 14 doctors, they managed to get to the right and left lung 100% of the time. Thank heavens. They got to the right, the left, right lung. They started to make errors at generation 2 after entering the lung. And in generation 3, it's getting pretty troublesome here. Generation 4, it's pretty bad. And since for peripheral nodules, they often have to go much deeper than this, this is pretty disconcerting. And an additional part of this is that we actually also ask them to rate their confidence, and they tend to, of course, be too confident. They're overly confident in this mediocre performance. So we did this study. Okay, this is truly a problem. So this is going to come up again, by the way. So we see mentally planning is not a good thing. So now, current practice in terms of how do they do this, how do we guide them? Well, they don't have a whole lot. They have fluoroscopy. Maybe some of you know what that is. It's basically doing a live chest x-ray, and it's 2D, and it's just the pits. It's not very good. And they use bronchoscopy, and they use their head, the mental plan that they've got. Let's just take a look at what's going on with this endoscope. So here's an endoscope. Put it into the body, and then you get this video. this video is not giving you a whole lot of cues on where you are geographically in 3D. You kind of get some very nice data here for sure, but geographically you get lost quickly. You start to turn yourself sideways. Before you know it, you really aren't going to know where you're at. And that bears itself out on this study, that we did, a second study with 12 physicians, a phantom study. This study, they had to go up to generation 8, go on more peripheral sites. But we did see how they managed to do for generations 3, 4, only 56%. They had a CT scan, they could take their time, they weren't under any pressure, but they were pretty shaky here. And that by generation 6 and 7 are down around 30%. So pretty poor performance. So planning and guidance without any help other than using the images is not going to work. So this kind of gives us some big picture view of this. You see what's going on with this. But this is another major point I'd like to make about this in general. This is true in all surgical procedures. In surgery in general, the doctors are very smart people, but their skill sets aren't necessarily the same at all in terms of how dexterous they are, how proficient they are in performing this. So this doesn't show up in the numbers I showed you with the 30% and so on. You'll see this come up again, but this is an issue. This is a major thing to try to look for and try to help come up with devices to help physicians do better. In our domain for the airways, a lot of the sites we're looking for, as it turns out, you're not going to see it in the video. It's going to be outside the video. It's in the tissue somewhere. That makes it challenging, and it definitely has a pretty big challenge to trying to know where to poke your needles to make biopsies. But the net result of all this is that they go in there, they subject the patient to this difficult procedure, and they end up failing in the procedure. And they might think the patient's okay, but they don't really know because their miss rate is so high. And I just sort of put this little addendum down here that there are also other modalities that are coming into play, like PET's a really good one, as we'll see, and ultrasound's very useful, and we work these things into our work, as it turns out. But this is sort of this, and a few of the numbers are kind of motivators for us. So our work, we're big image processors. We use computers, computer algorithms, mathematical algorithms. We've done a lot of stuff with for planning procedures, in processing, vision, graphics. I could add machine learning, but I'm not going to mention that much in this talk. Just stick to the basic, general, wide range of image analysis techniques here. We brought all this into play to help with this particular problem domain. So this slide right here is perhaps the most fundamental idea that kind of helps make our work useful. This idea of virtual endoscopy, which came about in the 1990s, and we're specializing into the chest, so we call it bronchoscopy for the chest. But basically, we have this fantastic three-dimensional 3D chest scan, three-dimensional digital image, like over here, for instance, this block of data, and it really is a pretty good copy of the anatomy. It really is well represented in there. So we can use this block of data and plan a procedure offline, without any worry, and we can explore the anatomy to our heart's content and preview the whole procedure. And another thing is we can generate these graphical views from that model, from that CT data, that look a lot like the video. This is generated from the CT using surface rendering, same camera model as the camera model that the endoscope has. So we can mimic the models, and by doing that, we can then bring the sources together. So this idea right here allows us to take from an offline world of planning and then bringing those guidance. You see these lines here, those are like center lines. The blue line, these are like paths that are going to lead to, say, a tumor that we want to plan. So that way they don't have to guess which way to go and get lost. So virtual endoscopy really has been the key. And I should say, like at this point now, these image-guided systems are used in hospitals around the world. Over the past several years, have become prevalent. And all the image-guided systems for bronchoscopy use this idea of virtual bronchoscopy for guiding bronchoscopy. So with this idea, using the CT data offline, we can then link this virtual world to the real world that's observed in the video during the live procedure. And that allows us then to start fusing data and then bringing in information to help make this real world procedure go well. So we do all this business with easier planning, no more mental trying to remember what you did. Guidance is real, much, much better, and we can augment their vision to help them do still a better job or do things that they wouldn't have been able to do before. So I'm just showing this one snapshot for first. This kind of gives a big picture of this idea. Real chest, real physical space. In a virtual space, this is a copy of this real thing, and we can extract this airway tree from this virtual space. We can get the interiors of the airways right here, these renderings, and these can be registered in the real video when the video scope is put in to get this real manifestation during the real procedure. So you see these are actually registered views, and once we do that, we can start fusing things and guide this guy here during the live procedure. So I just want to show a few of these early ones. We actually did show about the very first, one of the very first virtual endoscopy. This is like through a rat heart long ago when I was at the Mayo Clinic. Pretty crude data, although the resolution was 0.47 meters cubed. Dave Vining, this guy here, he also got credited for one of the first virtual endoscopies. It was 1994. I mentioned his name because he got a patent on this idea, and he managed to hold on to it for the better part of 20 years, and he made a lot of money. So good for him. I've met him a few times, and one time he had his lawyer going around RSA saying, you know, I have a patent on this. But so that's another story. This is like a later rendition as the data was getting better. We're going into trachea, human data, looking pretty nice here. And now our data is really nice. We can go much further than just the trachea. I'm not going to say a lot about this, but I just want to show you like a hardware figure. It's really simple stuff. We're not big hardware builders, but you know, we can get data from the scanners. We use this Matrox business to kind of interface video. We actually do have some things that allow autonomous guidance with foot pedals and things like that. And got this software stuff over here I won't say much about. We do a lot of our own custom work, but we use a lot of existing developer tools as well, of course. Keeps changing. It's a big job kind of with the software. I like to spend more time on this, the workflow. What do we do to kind of illustrate what we've done to kind of help improve on the situation that I outlined to you. In terms of planning, the CT scan, let's say a bit about that. I just have the one slide here. I was going to say more about this a little bit later on, but you see all these things here. We've had many, many papers published, so let's put some of these things down here, but we've done things to sort of help define these nodules nicely. We've got this live wireless business, extract airway trees, lungs, vasculature, thoracic cavities. So this has been a lot of work here. We've done optimal planning that takes into account constraints such as the device, the airway tree, and where needles may go and so on. So we've done that. So we have all this stuff. I'll say a bit more about this one aspect of it that we've recently done to help with this. The guidance phase, we can preview the plan. I'll show that. We can look on a tablet here and preview the plan. This is like looking at the procedure in advance. We get paper copies. Continuing on here, when they actually do the procedure, the phases of the procedure are navigating to the correct airway and localizing to the region of interest, the nodule or the tumor. This shows a kind of a quickie snapshot. This is something we had predefined as a small thing. Here's like our final destination. This is the real thing. It's actually been registered. You see a needle coming in here pointing to that location. I just want to point out, like the goal here is to kind of collect a tissue sample, hopefully a really good one. So let me just say a bit about the guidance here at this particular point. So I come back to this figure here. An aspect of trying to help use the procedure plan that I quickly say we can compute is that we have to link the virtual data to the real data. So that involves registration. Once we can register this data and all the stuff we compute to this real video, then we can do all kinds of help, like giving them cues as to where to go and what to see along the way to help them make decisions. So I'm just going to say a bit about this registration process here. So this is kind of a top level picture. Here's like the virtual model. This is the real model, like a real camera, the video there. Here's a virtual tree computed from CT scan, virtual camera. This video is kind of fixed. So we basically, as we're tracking along, as we'll see, We can move this space around to our heart's content to kind of match this, and we do match the camera models here for what it's worth, just to say that. So the trick is to actually do this particular registration. So I'm going to mention one method that we use. Maybe some of you know about image alignment and computer vision. It's this classic paper by Baker and Matthews and among others, where you have visual camera models. You kind of match up the pictures. It's used a lot for image mosaicing as well. We actually use that, but instead of having two camera images, we had like a one camera was the real video, the other camera was this virtual camera. So we had to bring in this extra thing called image-based rendering, which to say a bit about. But I just threw some math up here. I was multivariate calculus and iterative business here going on. A lot of offline computation. This inverse composition, if those of you that are way up on it, is a very fast technique, but we do a lot of offline calculation of depth information, gradients that are needed. Like those, you might have noticed those slides with gradients there. And then along the way, we're doing warping. That's a common aspect of these type of methods. Kind of go through the registration process. And one aspect is like taking the video and sort of transforming it to the space of the virtual. We only have one video frame, but we got lots of these. So we kind of come up with a way of mapping this to this image-based rendering process. And this kind of is involved in our mapping process along the way. So we used this technique, and we did a test with these 6 physicians. This is an early test, simple educational phantom, and we had them look at several ROIs, and we had kind of shallow here. They had the CT scans, and this CT scan for this phantom is pretty trivial. So it's an easier scan to look at. All it shows is the airway tree and light, spots to light up to show the where these. We put platinum beads on here, as it turns out. So it's much easier data to look at. And then they're supposed to then navigate the scope to each of those sites. So for these 6 doctors, it is quite a bit simplified test. This is their performance, how close they got. You know, they ranged from about 2.7 up to 9 millimeters in terms of how close they got. And just to sort of get some frame of reference, the size of a typical nodule is around 10 millimeters. So these people are making pretty big errors. And you can kind of see here the average error is about 5.5 millimeters. Pretty big standard deviation right there. So then when we used our guided system, we then had the plan, we had our system running, we guided them. You see these numbers right here, all down in the ones, how close they got. Also, you see that the standard deviation got down to 1 range. This slide, I think, this particular result at this simple level might be like the most important result. Like for image-guided systems, what you want the system to do is you want to, first off, equalize the performance of the doctors. I mentioned that the performance varies a lot. Well, this shows that we can kind of like get around that problem. And basically, they're all performing about the same. So that's a huge thing. The second thing, of course, is that the performance is much better. Performance has improved dramatically here. So this is just a classic, fantastic result for the success that image guidance can have. And it makes it more feasible to kind of do these type of procedures for more patients, because then you can have more people other than just the resident best physician in New York State do it, as opposed to Joe Doctor who lives in some other place in New York. Now this was a further test. This was a much harder test. We had 12 physicians doing this. We again had a phantom. These sites now went through generation 8, and a CT scan was a real CT scan. And it was a harder test, more like what the peripheral bronchoscopy would be like for look for lung cancer nodules. So for these 12 doctors, if they did the standard approach, they had to take their time. They're not even under this time pressure. It's not even very real. They have to sort of like take their time here. They're only hitting about 43% of the sites. And you see their standard deviation here. Basically, their standard deviation is around the size of the nodule, about 1 centimeter. And note the huge variation here. So their error is huge and their variation was huge. This right here shows the variation in the physician performance. This shows how bad they all are, regardless of whether they're good or not. So here is our result, 94%, nearly 100%. You see our variance and error goes almost down to as small as you can get. A person's not gonna be able to do much better than 2 millimeters. A person's gotta like maneuver this device and stick a needle there. The only thing that's gonna do better than this is a robot, and that's coming soon. There's already a robotics company. But this is a huge result right here. So I'm kind of at this point, or earlier on, just before this, that I have to sort of start my own company. I'll say something about that a little later on. Here we are in the surgical suite. This is like our very first live study back in the early 2000s. We've changed equipment some since. I have a couple early examples here to show. First off, blue navigation routes. We need to lead them a long way. We have this like little endoscope model. There's a needle. There's a target nodule. When we lead them along, the airway tree is really good for this because you can lead them from one bifurcation to the next. It's like, you're following MapQuest, you have your directions, you go from one direction to the next. The airway tree is a natural for that. So we kind of treat this as like a navigation. So we save the previous view. So this is like a base camp view. We now call this the base camp. This is the previous view. Now they're going to the next view. So we registered ourselves here. They're following the blue line. Sometimes we'll put it over here. Sometimes we don't. Actually, this works so well that they can just follow along pretty easily. Here's another short one, kind of like you see the needle pointing toward a nodule, and we're at the final site, and you see the needle actually coming in here. So, lots of examples like this. I'll show a few others a little bit later on. I just wanted to show this registration method. This is this inverse compositional. Big thing here, this method is super fast. It could go through theoretically 300 video frames per second. This is on a relatively older computer now. It should be better than this. So this is way over real time. So that means that if the doctor's moving their scope, conceivably we could just follow them all the time. So this is just kind of showing a video of this. So the physician's moving the scope here. They're following the blue line. The blue line is in front of them. And this thing's following right along, and there's this blue arrow coming in, and they reach the site. Kind of nice with this. The nice thing about this is it does kind of like go forward, but it's still fairly easy to do this. But this method was really quick. So another result that we had here, we looked at a number of patients. We had a 30-patient study looking at these peripheral sites. So we're really using a pretty small scope. The airways start getting kind of narrow out there. But we had our system. There's another system that was going on with Olympus, and we compared our results to them. They were not able to get as deep as us. Both systems are around over 90% accuracy. Navigation success means reaching the site. I'm not saying anything about tissue samples, how good it is yet, by the way, that's going to come. But there's this. But we already see that it's a lot harder to go more airways. So our performance really is quite a bit better here than this particular system. So we have this pretty big advantage here. So now kind of moving on to the second part, I'm going to kind of add some other modalities. I'm going to add PET, I'm going to add ultrasound. PET, as we'll see, is a good modality for really finding the places that are suspicious. And ultrasound is really good for seeing things outside the airways that we can't see otherwise. And I'm going to kind of highlight the idea of getting optimal tissue biopsies, making sure I can really get a lot of tissue. And also going to talk about the guidance process with this multimodal world. We can now do multimodal virtual bronchoscopy. We can have a virtual video and a virtual ultrasound. We have to register to the real video and a real ultrasound. Let me kind of get into that. So the ultrasound, there's two types of ultrasound. We're working a lot on this one, this peripheral one right now. I'm not going to say a lot about it. This goes into a small scope. It goes way out to the periphery. I'm going to focus on the central one. We have these integrated devices where you have a video camera, a needle coming in here, and here's the ultrasound probe. We press against the wall, so you get images that look like this. So there's a node right there. The video is also available there. So we have this is really a multimodal device. So a lot of the time when we're navigating close to the site, we're using the video, and then we want to actually look at the region here. We then push the ultrasound against the wall to see the actual region of interest. So I show that here. Here's this model of this device. And then over here, I've got this little video. I'm not sure if the lights aren't perfect here. The lights are on. But there's the video. You can see there's a region. There's also video here. It's a picture-in-picture view. Sometimes we'll switch these views ourselves. We can do that, and we'll process both of these. But we're going to bring both of these together here. The ultrasound, the big advantage is that it gives information on these sites that are outside the airways that you cannot see in video, which actually is true for the large bulk of sites. So the ultrasound is kind of a major modality you really want to be able to use. Now, another source of information is this PET image. So here's the CT. We have our chest CT, beautiful resolution. You see a nodule here. Only problem with this is that you don't know it's cancer. All of us may have these types of things. And when they've gone through screening studies in the past, they found like 95% of the nodules lead to nothing. So you want to have some way to like, okay, CT is so beautiful. Is there a way to get more on this with an image? Well, PET is really a good modality. Lousy in resolution, but it's highly specific. So it's a great complement, and it's pretty pertinent. And these scans tend to be these whole body scans. They're also, the patient's allowed to breathe, so there's a lot of motion. That's not terrible because we can do deformable registration, as I mentioned. I'll just show, yeah.
So what is the phenomenology for the PET scan and detecting cancerous cells? What is the
Well, it's a positron emission tomography, and they do this thing, it's dioxyfluoride. It's like a fluorine, this is dioxyfluorine something or other. The patient will take some kind of drink something, and then when the PET scan is on, the particular radiation that the PET uses based on this dioxyfluorine 14 is able to detect places that are sensitive to that agent that was brought in. And it's very specific. So like this is not good to see. Now here though, like there's all this hazards about people have to cooperate with their diet and so on, but I'm not going to get into that. So you got this nothing down here, down in the digestive tract. That's nothing. I didn't want to pop up this little movie of what this whole body PET looks like. It's 3D. It's whole body, you know, nose to knees. That's how they do the scan. You sort of get an idea. It's 3D. Not such great anatomy, but actually there's enough stuff there that we can bring the PET data in with the CT. And actually, I should point out that we have this scan. We have a corresponding whole body CT scan. We do have that. Although it's not the greatest resolution, but it's satisfactory. So with that PET data and with the CT scan, we can just focus on the chest part. There's a lot of geometric stuff here, all this stuff with coordinate systems and so on. Maybe somebody had to deal with all this hassle, but all this coordinate system business here to get the PET scan doesn't have the same coordinate system as the CT scan and so on, but we took care of all that. But we kind of take this data, it's done free breathing, so when if you're breathing, your lungs are empty, so your lungs are a lot smaller. When the chest CT is done, they hold their breath, at least so it's fully inflated. So the geometry is fairly different. So we can't just do simple registration, we have to do deformable registration to kind of make the data get mapped to the right place. So we go through a two-stage process, skipping all this coordinate system business, rigid to deformable. I'll show that on the next page. So like we have these two scans and we do this rigid registration, gets 90% of the job done, although none of the real work is done yet to get the tissue in the right place. Then we do the deformable registration. And as it turns out, this ends up actually giving us resolution that's satisfactory to plus or minus 3 millimeters. So that means we can bring in this PET information, these lighted spots, and show them. So we do all kinds of renderings and so on with this, and I'll come up in a few of the slides, but we can make these multimodal renderings that combine PET and CT. So here's the CT data with ROIs, but then we have the PET information brought in there as well. We can fuse CT with the PET. There's actually PET in there. There's a spot right there lit up, and we can make virtual PET bronchoscopies. We can do that a little bit, and so on. We can now bring in this highly diagnostic information with this process. So I showed you the virtual space and real spaces that we try to bring together. Before, all we had was CT and video, but now with the PET imaging and also now with the ultrasound, we have this sort of higher dimensional situation. So the virtual space here has a PET scan and a CT scan, and we can make a multimodal virtual bronchoscope. I'm using that device I mentioned where there's ultrasound here, the blue arrow looking up there, video over here. We have the video, this is a virtual ultrasound. It's the same geometry as the real ultrasound. This is actually the PET data, this is actually the CT data. Although we can put other things there, as we'll see, we can put the PET there. We've been playing around with trying to model, actually making the EBIS out of it, but we don't really care about that. But we have this multimodal virtual space, and we also have multimodal real space. The video is prevalent a lot of the time, and at the very end we need the EBIS, the ultrasound, endobronchial ultrasound. So now we have this multimodal virtual bronchoscope. We can bring all these sources together. So one thing I do want to talk about, I didn't say a lot on planning, one thing we've recently kind of finished is this idea of trying to get really good tissue samples. We can get them to the right airway, we can get them pretty close to where they want to go. We had been showing this, like the other stuff I showed you, use this for the region of interest. This is like some nodule that's outside the airway and you see it projected onto the wall when you're doing a procedure. Only problem is you don't really know like how much tissue is there. Well, we've kind of come up with an approach to kind of really be able to sort of say the best place to sort of poke this so we can get really a good tissue sample. So I'll say a little bit about that. So we have started to use this business right here. So we kind of model this. This is a lot of math. I'm going to skip through all this. I know you're not going to get any of it, but at least you get the idea, oh, he knows some math here. So we got to model the needle, all this geometry. Now, this shows the device, the needle coming out. Now, this is not a perfect process. You expect that the doctor is going to be perfect. Somehow there's going to be, they might think they're going somewhere, but you can model this as some sort of a cone of uncertainty. So you can kind of have a multidimensional PDF function here. It depends on where the needle could go inside of some cone. So we have a PDF for that. So that gives us a space. And there's also, you see that nodule there as well. And we can kind of set up a line integral or where the needle's going to go for any given direction inside that cone. And then we can then bring in the PDF right here for that direction and look over all the angles, so then we get like the expected depth of sample. We can also figure out the maximum depth of sample. We do that. There is going to be some best direction here that we can compute, but there isn't a chance on earth the doctor's going to hit that spot. They can get within the cone, but they're going to hit this exact spot? Forget that. So you kind of like to sort of think in these terms and then present that view that they get an idea how it's getting worse and better. This just sort of shows it digitizing this. Actually, it's pretty sophisticated digitization. I just figured an equation. It was kind of pretty slick what we ended up doing there. We have a lot of constraints we work into that optimization right here to kind of figure out the best pose for the device. We're trying to lead the device to a certain place where to stick the needle. And the computer vision people, you know, like what that means, like you have a camera that's some position, some pose. So we try to find that to give the best tissue sample here. And we work in constraints such as what's going on with the device. We're also interested in safety, by the way, because in the chest there's lots of vessels. You don't want to puncture the aorta, the person could die, or the main pulmonary artery. So we watch out for those things. We have a safety margin built into this so we do things safely. So we want a big tissue sample, we want to be safe. We want to make sure the bronchoscope can fit. So that kind of figures into this as well. So this kind of shows, like, so we can compute that stuff, but then the graphical part's also important. So like during the procedure, as they're moving the device, and as they're following our guidance, they can see like, oh, we're getting close. Okay, not good enough yet. And the indication that the needle's really missing it, but they'll see this, and then if they actually hit it, there's this. We can show this stuff in our plan. And in reality, they're seeing, okay, if I put my real needle there, that's going to be a good tissue sample. This kind of just shows the uncertainty of this a bit. Also, of course, the varying shape of the ROIs. So we kind of compared our method to a few other methods. And there's really two things here. Do you hit the node? You want to, if you're looking for a particular lymph node or cancer node, you want to actually have your needle pierce it, get some tissue. Well, at least in our test, we're getting 100%. A few other past methods are in the 70s, so that's okay. The big thing, though, is you can hit it and not get much tissue. So there's this thing that people use called biopsy adequacy, you know, how much tissue you get. It's a percentage, where 1 is sort of like the maximum you could get for a given object, given its geometry, if you look at the principal axes. And 0, you missed it. So I put 2 numbers here, 0.05, because sometimes doctors say 5% is an adequate sample. That could be somewhat doubtful. We got 100% of those. And these other methods, this is a much more recent work. These are different sized needles. This is a thinner needle, as it turns out. It doesn't get as much tissue. Bigger needle, more tissue. Now, it's actually interesting to look at the idea of getting a 30% sample. Now, I see 76% there. That's actually really good, because it turns out if you have a cancer nodule or lymph node at some particular location, you are not going to necessarily, it's not going to be feasible to hit the most optimal point. So it's actually kind of good to get a hand on this. And actually, one of the things that I don't show on here is that for our set of lymph nodes, at least with our safety margin we had, we said that several nodes are not even safe to go for at all anyway. We shouldn't even biopsy them. But that's the doctor's discretion. But you don't necessarily expect this to be 100%. That's really, that probably will not be able to happen because of the physical space that you're constrained to and the devices involved. But clearly we're doing pretty well here as well. So this is a nice thing here. So we can hit the sites, and also when we hit the sites, we have a really good chance of really getting a good sample, or at least as good as you could do given all the constraints that the patient's body and the devices are imposing on it. So now the virtual bronchoscopy with the multimodal. Here's the multimodal virtual bronchoscope, real video. Oh, now real ultrasound. And the simulated virtual video and the simulated ultrasound. You got the lines out here to kind of indicate the fan-shaped view of the ultrasound. We got this thing going on here with the ultrasound and the video, the real and the virtual. Let's just kind of get right into the actual guidance here a little bit. All kinds of stuff. Here's a virtual multimodal bronchoscope. Video down here, real, virtual, real EBIS, virtual EBIS. We're kind of maneuvering our way down toward this region of interest. We've been moved away. This shows that fan-shaped field of view. We know that shape because we know the device, so we can graphically show it. We're getting close, so that's what I say here. They've navigated away. It's mostly just only looking at video. They haven't bothered to engage the ultrasound yet. But they've gotten to the point that, oh, okay, it's starting to light up here. And we have all this fun stuff. We haven't actually used this in real life. I don't think doctors don't want all that stuff. It's just fun for video games' sake. This is useful. This is certainly useful. Actually, this panoramic view that extends further is really good. But this is kind of telling us we're getting warm. Now, the device has to be rotated in place to engage the ultrasound. So we're going to take this view and we're going to rotate it. So I'll just show that. I'm kind of brushing over this. So what's happened now is that this has been rotated and it's now really engaging the ROI there. You see the ultrasound field of view hitting it. You see there's the ultrasound view hitting the tissue, avoiding the big vessels. We got to put these obstacles on there. This is just like computer vision, you know, navigating autonomous vehicles. We're doing the same thing here. We got obstacles to worry about. And here is the virtual ultrasound. It looks like it's sitting right on top of this green thing. We planned this guy. We defined this thing. We see we're already smack dab on top of it, ready to probe it. And this little video simulates pushing the virtual EBIS onto the thing, and you see like, oh, look at that sample, it's looking great. So once the needle comes in, and the needle, this is the needle coming in, right? That's actually gonna be the real needle coming in at that angle. We know that geometry. It's gonna hit that tissue nicely. So that's kind of like final view here. It's kind of a lot of stuff, you know, but well, this is just for fun here. Here's the real EBIS, it's been engaged. There's that little ROI, we got it. We did some registration here, and I just kind of give a snapshot of registration, normalized mutual information, simplex optimization. NMI has been used for like medical image registration in other domains. We used it here for this virtual ultrasound and real ultrasound. And this just kind of shows like what we can now show. They have the real ultrasound view. That's over here with this ROI painted on it. We can show this view. You see the vessels. We show the PET. We can fuse the PET and the CT, and the doctors love this. They say, oh my gosh, that's fantastic. I put my ultrasound there, I think I got it, and the PET's like, it's like a Christmas tree here. So this is really a nice thing to bring in. And it's got a composite view, very busy view. I'm sorry, I had a lot of stuff on here, but ultrasound's engaged. This is before we rotated the device, and the device is rotated to the left. You can imagine this thing going over there, sitting on top of it. And this sagittal view cutting through the chest is, yep, we're smack dab on top of that ROI, all right. The ultrasound sees it, PET sees it. This is a success right here. So I think I'll say a bit about my entrepreneurial stuff, because this stuff has gone well and has led to commercial systems. I don't know if some of you might be interested in this, kind of trying to commercialize things. It was clear that we had a big market and the problem was there. People spend a lot of money on these things, and so since money tends to drive things, it seemed like it was really good to sort of try to do this at the time I got into this. So we had the real world problem. We had the market scoped out, that's for sure. So like we were doing all this stuff in the university, you know, in our work in the lab with patients, and we actually got it to patients. So I started my own company. We started protecting intellectual property. And some of you might get into that. I don't know if, how much of that's done here at Penn State. They aggressively apply for patents. And so that's a long process, but you need to kind of have some intellectual property you own so you can block other people. So we were doing that. And we then do some small studies. We did do phase 1 studies. I ended up having a fair bit of money for my company early on from small business grants, SBIR grants. I had employees, but I was tied to the university as well. So we were kind of a team working together on this. And things were getting to a point, I started talking to venture capital people, because this is fine, but you got to get a product out of it. You has to actually be deployable, that doctors actually, not only didn't want to use them, but they can actually pay for them being used. They can actually bill people for it. So that means you got to bring in FDA, you got to work and do bigger studies at clinical sites. So I got into this, and I got a company involved, as it turns out, through talking with VC types and then other companies, and people started calling me. I finally got a partner, and they did this stuff with the making an actual product out of it and getting it to the point that it could be used clinically and proving it with other sites. And now this company has gotten up to about 100 employees, and they've tied into another big surgical company recently. I think Christian might know about it, Intuitive Surgical, that sells Da Vinci systems. That's really been a great thing. So there's, I took a number of leaves of absence, by the way. It takes really a lot of time, so I took unpaid leaves. I had my own money, but I thought, okay, this is fun to do, and I think it's going to work out, so I did that. So that does take a bit of sweat equity there, that's for sure. But this company, Bronchos Medical, they've raised a lot of money. They have, like I say, up to about 100 employees. They have various products. They've gone through the FDA process, and products are there now. They're sold worldwide. Lots of patents have been applied for and then granted. We have international patents. And we've had various systems, like a planning system, and they've changed this. This is a newer system, using some of these kind of things you guys might be playing with here and so on. You see a lot of images that I kind of showed you that are sort of on there. And I just like to see this picture, this big crowd here, this big medical conference. These people like looking at this, oh, how about that? Great. Hopefully they bought something, but I'm not supposed to say that. I got my conflict of interest statement right here. I'm not really trying to sell anything. My group, NIH support. I have a really great clinical team I worked with for a long time at Penn State. And that is my whole talk. Slide over.
Thank you so much for a very interesting, exciting presentation. Any questions from the audience? Dave? Yes.
What's the limiting factor? Is it the resolution of the imagery that you're using? Is it the accuracy of fusion? Is it, what's the limiting factor that says you can't get to 10 millimeter accuracy here?
Well, I don't think you get more than accurate about 1 millimeter because the needles, the diameter of the needles are about on that order. The CT scan resolution is really high. It's plenty sufficient. Probably in terms of being able to go to any location in the airways, it probably is the geometry of the airways and the devices, but they do have flexible needles. They have this. So really, I think these systems are used worldwide now. They really are. One thing, this highlights some of our work that we're kind of getting into, like with cancer, they should be able to do a really good job on a single cancer nodule, the thing that shouldn't be there to begin with. But then these guys here, these lymph nodes, they're there. And I don't know if you know about how cancer works, but when cancer gets in the lymphatic system, then it's curtains. That's when it starts to go all over the body. So in principle, they have to sort of sample all these sites, or at least get to the disease early enough. So right now, there is a big emphasis on kind of going back as early as they can. The staging, the screening idea that I mentioned, which is still ongoing in a big way, trying to roll it out, that is going to change the patient population. So that really ought to be a huge help to have them get diagnosed a lot sooner and be able to treat them. So I really think like this 15% survivability really should go up at some point, at least for the people that they actually work on. But I actually think the technology is very, and I did allude to this briefly, but robots are coming in this. There is a company that has a robotic device out. So they need planning. They still need these mechanisms. That has to have this.
Yeah.
I mean, you have to have a doctor there to babysit it, to make sure it's on track. But the robot, certainly, I was talking to someone, a robot has no emotion, no stress. They can be very precise if the robot is well made. And that is coming up. This one company that is doing this, they had like about $90 million VC capital for the company. They have this device out, and it's a very slow system, so it's not very practical yet. But it will be. It's for sure going to happen. So the robots can take over, and they can conceivably go around and sample all these sites.
But the guidance is still needed to the robot.
Absolutely, yeah. They have to sort of they have the same constraints. It's the same planning problem. A robot has to have this plan, this precise plan. And they're going to need they probably need the live data because the chest. That's a factor actually a little bit. There's a lot of motion in the chest, so this is a stop action shot. So things can move. So you really have to have the ultrasound. Not always, but it helps to have as much live confirmation as you can get.
Real time.
Yeah.
Any other questions from the audience? So when you go down to like 8th, 9th generation, you mentioned the airways. How small are those airways, and can a regular scope go all the way down there? Plus,
Yeah.
you mentioned the multimodal scope that has the ultrasound transducer at the end and the needle, and so all of that has to be instrumented into a single scope that you're trying to go all the way down.
Yeah, that one device can't go more than 5 generations. But the airways, we've gone to deepest generation 13.
With a regular commercial scope?
They have different diameters. So we did that with a diameter scope that was around 3 millimeters. Those can pretty much go as deep as you need to go. And they have a working channel to stick the needles into, or the ultrasound probe into. And we're working on that part right now with the periphery. This is the ultrasound stuff I hear was focused on the central, the bigger device.
Right.
But the little peripheral device, that can go way out. That generation, we went to generation 13, and I think theoretically it goes to 19 or so, 18 or 19. It's this well-known Weibel model. It's well-known, but it can go pretty far out.
Yeah, I just didn't have any information. I didn't know how large the generations are. But 3 mils is actually pretty large for a signal generation.
You say part of the planning process isn't necessarily going as deep as you can. It's trying to find the airway that's going to actually allow the needle to be able to go through the tissue and hit the site.
Can
So
the
you might
needle go
actually,
in?
you might actually be over here further back, go like this.
Right.
So there's this trade-off of how far you travel through the tissue. But that's
So
all
now the
good.
needles go through, like, without this device that you mentioned, the needles go through from the outside, and do they puncture through the lung, or do they still do it through the airway?
Oh, this is actually in the airway. Oh, the needles are
Okay, so-
in the bronchoscope.
Oh, okay, so
Yeah,
I see.
they're into the airway, they're in that location, they might travel a couple centimeters.
So you don't want to puncture through the outside.
Well, you don't want to puncture the lung because they could die.
Exactly.
It's, yeah, not necessarily, it's called pneumothorax.
Yeah. Cool. Any other questions or comments from the audience? All right, well, thank you once again for a great presentation.